So welcome everybody. Today we have Marco Merkli, and he will talk to us about dynamics of entropy in bipartite quasi-Hermitian systems and their Hermitian counterparts. So when you're ready, Marco, go ahead.
I think I'm ready. Thank you very much, Andreas. So I guess nobody knows me or my collaborators or our names. So I should maybe quickly say who we are. This will be a collaboration. This is a collaboration with Abed Al-Salam Abu-Moisi. He's a graduate student at our department, and a colleague of mine, Graham Cox, who is a faculty member of my department. We are at Memorial University in Newfoundland. That's the very east coast of Canada. And we're in the mathematics department. So Graham is really an analyst, a geometric analyst, and I'm trying to be a mathematical physicist. This topic is new for us, for all three of us. I have mainly been working on the mathematics of open quantum systems, dynamics of open quantum systems. I've been developing tools to show the validity of the Born and the Markov approximation, actually, of open quantum systems. So this topic of PT symmetric quantum theory, quasi-Hermitian and pseudo-Hermitian and non-Hermitian Hamiltonians and so on is all new for us, okay? And so a while ago, the trio of us, we decided that it would be interesting to start learning about this topic, and we read a few papers. And of course, we came across several papers of all of you guys, and in particular a paper of Frith and Fring in 19, which is, the title is something like Eternal Entropy in Non-Hermitian Quantum Systems. And read this paper in detail, and we had some questions about it, really. And so out of those questions grew this project that I'm going to talk about. And I can say that being new in the field, I contacted Andreas, not knowing him, and he was very gracious to actually take some time for an hour, and we had a video conference and asked him all kinds of questions, and yes, thank you very much. And then after a while, after we posted this manuscript online, Andreas invited me to give the talk here, so I'm very glad to be here. Also a little bit apprehensive because this is new for us, and so, you know, maybe you guys would say, oh, well, you didn't understand this correct, and all of this is wrong. Anyway, so this is posted, this work is posted on the archive. It has been posted and submitted for publication in the summer, actually. And we haven't heard from the journal back, except that they have some referee reports, but are looking for more. Okay, so this has been quite a while since this has been posted and submitted. Okay. All right. So, of course, we're looking at quantum evolution, and the quantum evolution is given by the Schrödinger type equation, right? I allow myself to put h bar equal to 1 throughout. So the derivative of psi is h psi. This all happens in a Hilbert space. The initial condition psi naught is a vector in a Hilbert space. And the Hilbert space has a given inner product, which is denoted like this. And H is, of course, an operator, a linear operator acting on this Hilbert space, the Hamiltonian. Okay, and then, well, you can look at two kinds of situations. The usual quantum dynamics, where the Hamiltonian is Hermitian with respect to this given inner product, or the quasi-Hermitian situation, which is what we're going to be interested in this project, which is the situation where the adjoint, or the dagger, H dagger, is equal to eta H eta inverse, where eta is a positive operator, positive with respect to this inner product. So it's a Hermitian positive operator satisfying this equality here. And such H's that satisfy this for some so-called metric operators eta are called eta quasi-Hermitian. Okay, and in the quasi-Hermitian case, the physical Hilbert space is the old one, H, in terms of the set of vectors, but you change the metric. You just put in the old metric, which was just this, right? You stick in here the eta operator, the metric operator, you get a new inner product. And with this new inner product, you get a new Hilbert space, and you call this the physical Hilbert space. And if H was eta quasi-Hermitian, then it is actually Hermitian with respect to the new inner product in this new inner product space. Okay, of course, the adjoint now is different. And so this is the adjoint denoted like this with respect to new inner product. Okay. And then in this new Hilbert space, H is Hermitian, so it generates to a usual unitary dynamics. And you know, this is just a Schrödinger equation in this Hilbert space. The solution or the evolution of a wave vector psi of t is just given like that. Okay. And when you look at averages, you have to use in this physical Hilbert space this new inner product. And then it turns out that density matrices look like that. So there are vectors, or this is a density matrix corresponding to a pure state. It's given by this vector, but then you have to correct with this eta to make this actually a true density matrix, trace one positive operator on this physical Hilbert space. Okay. And so it turns out, of course, this is well known, that to a quasi-Hermitian system, you can associate a Hermitian system. In fact, you can associate many Hermitian systems. And how does this go? Well, you have a quasi-Hermitian operator H, so you are given a metric, which is a positive operator. Being a positive operator, it's always written as S dagger S for some operator S. And then this is the new Hilbert inner product, right? Well, this is S dagger S. I can take one S dagger over here. And so the inner product is actually written like this. And so you see that this S operator produces an isometry between your physical Hilbert space and the original Hilbert space on which your H was eta quasi-Hermitian. Okay. And then you can transport all the quantities between these two spaces via this isometry. And for example, the original operator H will become, when you transport it into the new back, will become this operator small h. It's just transferred by this transformation. And this one is Hermitian on the original Hilbert space H.
Can I ask a question?
Yes.
You said it would create an isometry.
Yes.
But the problem here is whether or not S is a bounded operator. If S is unbounded, then I don't know about there being an isometry, and I don't know that that's a good mapping. So that is the basic problem here. This is not a trivial issue. This is an important issue.
Okay. Okay. I take note of that. In fact, H is S typically is unbounded. Yes, we're actually going to look at finite dimensional systems, and so this.
Right. If you deal, that's right. If you deal only with matrices, you don't have to worry about this.
Yes.
But therefore, this takes this out of the.
Yes. Yes.
This takes us out of the realm of universality at all. I mean, this doesn't obviously work for a continuous quantum system defined by a differential equation. Okay, a Schrödinger equation.
Okay. Yes. Thank you. So, okay. So this is not in all generality, right? In my application, we will deal with finite dimensional systems actually. And so this
right. So it's not even close. This is just finite dimensional matrices.
Yes, that's correct.
Okay, fine.
Mm-hmm. Okay. And so the Hamiltonian transforms like this, and states transform like that. This is the state on the origin. This is the state on the physical Hilbert space, and then you can transport it back into your original Hilbert space. It will look like this. And so you get two different kinds of states, the round phi states and the psi states. And the dynamics, those of the phi states that you have transported back, just evolve according to the Schrödinger operator, the Schrödinger evolution with respect to the usual now Hermitian in the original Hilbert space H operator H. Okay. So even in the finite dimensional situation, this correspondence of you give me a quasi-Hermitian operator and associate to it a Hermitian operator is not unique, of course. There's two sources of non-uniqueness. First of all, the metric operator is not unique. That is a well-known, of course, and understood thing. In fact, the metric operator is not unique, but it is determined once you determine a certain family of operators that are all eta quasi-Hermitian with respect to the same eta. That fixes the eta uniquely up to a multiple scalar. Okay, and so this means that if you, in your theory, fix an irreducible family of what you would call them observables, because they're supposed to be self-adjoint, Hermitian, then the metric is fixed. Has been known for a long time. First, I think, was shown by Scholz in '92. Okay, and here's an explicit example which we will actually use. If your Hermitian operator, and you see here it's finite dimensional. Sorry, if you have an operator which is given by this here, where let's say En are real eigenvalues, and phi and psi n are states, vector states, and they form a biorthonormal basis, then all the metrics associated to this turns out to be quasi-Hermitian, and all the possible metrics are of this form here. Okay, namely you take these vectors, form the projection, and then you add them up as you wish with arbitrary, strictly positive weights. This has been well known for a long time and used by probably all of you many times. So here are a few papers in which this is used. Okay, but so that's fine, right? If the metric operator is not unique, but then you could say, as I understand, well, if you fix the physics, that means you say which observables you want to be actual observables, then you have fixed eta. Okay, so you remove this sort of non-uniqueness there. But even if one eta is fixed, you still need to take the square root s, right? Let me scroll up again, sorry. This s here that makes this isometry is actually a square root. And I say a squared of eta because the square root is not unique. So even if eta is fixed, you can have many different square roots s of eta, right? And in fact, if this is the condition on s, which it is, s dagger s is eta, then the general solution is that s is the square root of eta, by which I mean the unique positive operator that squares to eta. And then you can multiply this with an arbitrary unitary. All of these guys are exactly the operators that do this for a given eta. Okay. And so S can vary because you can freely choose W as you wish. And so correspondingly to each S corresponds this Hermitian operator H. Well, this will depend on W as well then. And so all the H's you can produce are of this form. Okay. It is true that, you know, if two different people choose two different W's, well, you will get two different H's, but all of these H's are unitarily equivalent, right? If I change this W into a new unitary, I get a unitary equivalent H here. But I think our point is that in open systems, the choice of W could actually really change local behavior or local properties of the system. If you have a bipartite system, for example, and the W mixes up the components, then you would get globally unitarily equivalent Hamiltonians by different choices of W, but locally they could vary. They could, you know, there could be some entanglement that is going to be induced by a specific choice of W. Okay. And so if you look at open systems, let's look at bipartite systems of the type system and bath. So the Hilbert space has this product structure. And then you may be interested in looking at the reduced system density matrices. So you obtain those by tracing out the degrees of freedom of the bath Hilbert space. Okay, so let's look on the quasi-Hermitian side. That's kind of the original problem. Let's say you have a quasi-Hermitian system, a metric is given fixed. This is a state you're looking at. Then you reduce the state to the system part. So you take the trace over the bath, and then you get this reduced system density matrix. And you do the same thing on the Hermitian side. There you choose an S. This is the corresponding density matrix corresponding to this, right? Then you take the trace over the bath, and what you get is the reduced density matrix of the Hermitian system. Okay. And if you do that in examples, and we will see such an example, generally the following happens. Well, this here is actually an operator which generally does not have real eigenvalues. It generally has complex eigenvalues. And the eigenvalues of this depends on what kind of metric you choose. Okay. So this is not a true density matrix because it has spectrum that's not purely positive. And even if you can find metrics for which this is actually a true density matrix, and in our example, this happens for specific metrics, even then you can, so then this is a good density matrix, right? Then you can compare the von Neumann entropies of this density matrix and this density matrix, if you wish. And you see that in general, they're not the same. They're not the same because the density, the spectrum of this guy will in general depend on S, which involves W, and it generally depends on W.
We have a question from Eric. Eric?
Yeah.
Yeah, so I wonder about these two trace formulae. So usually the trace is cyclic, so you can move operators around. So I would guess then that you would be able to move the S on the right, which is now on the left, to the right-hand side, and S dagger, S is eta, right?
Yes, you are right.
And I wonder,
but
why these?
No, you see, well, this is not, you see, this S here acts on the full Hilbert space, like acts on the system and path Hilbert space. Okay, so the point is that this is an operator on the total Hilbert space, which is H system times H path. And here, I only take the partial trace. So I don't have cyclicity because this operator is not in this. This is the partial trace only, right?
Yeah, and I'm not that much accustomed to partial traces, but I hope that these would still be cyclic.
No, but what you're saying would be correct. If I took the full trace, then it's cyclic and these two things would be equal. I agree. But you know, I'm only taking the trace over part of the full Hilbert space. And so it's not correct that I can move this over. It's not correct.
Okay. But it would also not be possible to rewrite the left-hand side, or is that meaningless?
It would also be possible what?
Would it be possible to decompose eta on the left, or is that a meaningless question?
Well, you see, if eta or S were of product form, let's say if this was of the form S system, well, that's unusual notation, unhappy notation, but times S path, then yes, the S path part, I could move from the left to the right here. You're correct. Okay. So if this is decomposed as a tensor product, so it's a separable operator, whatever, then this part here, because I take the trace only over that part of the Hilbert space, can be moved over. Okay, but in general, you cannot.
Okay.
If anybody else has a better explanation, they can certainly jump in, but it is not correct to move this over. It's not correct.
Okay. Thank you.
No problem. Okay, so that's kind of a general consideration, but it is true that you have to be careful when you take this partial trace, you may get an operator which is not positive definite. And even if it is my point, then these two objects, they do not have the same spectrum. And so their properties of entanglement and von Neumann entropy are maybe very different. So we decided to, so this is now for the concrete system that we're looking at. This is taken from the paper by Andreas and Thomas. And here's a picture. You have a single oscillator, the dark one here, which is coupled to n other oscillators, these guys here, and they form a bath. So the single oscillator has creation and annihilation operator denoted by A, and then you have capital N bath oscillators indexed by small n. And this is the Hamiltonian that is proposed in this paper here for this coupled system of n+1 oscillators. So here you have the total number of excitations, the one from the single oscillator, and then added up all the excitations of each of the bath oscillators. You give that a frequency nu. And then you have an interaction between this guy and all the other ones. And what's the interaction? Here you have a sort of a coupling constant. It involves, it doesn't have to, but it's chosen to involve the number n of bath oscillators and some two coupling constants here. I will come to that. But the point is that you can exchange an excitation between this central, if you wish, oscillator and all the other guys. Okay, so this is here you annihilate a collective, and this is sort of the collective annihilator of all bath oscillators. This is the definition of this operator Q here. It annihilates on each of the bath oscillators, and it's normalized. And then you create instead, you transfer an excitation to the system, or vice versa. Okay. So then we have these two coupling constants, G and kappa. They're both real. All parameters here are real. But the point is that here it comes with a plus and here it comes with a minus. So if kappa is equal to 0, then this is just a Hermitian operator, right? But if kappa is not equal to 0, then this is not a Hermitian operator. And so Fring and Frith, they show, no matter whether kappa is 0 or not, this is a PT symmetric operator, okay? And so you can feel what's going on for small kappa, right? You're close to the Hermitian situation. So you're going to be in the PT symmetry unbroken region. And if kappa becomes large, then this is far away from Hermitian situation. So you will be in the PT symmetric broken region, okay? So actually, this is what Frith and Fring show, part of what they show. So H is PT symmetric. And if kappa is small relative to G, then you are in the symmetry unbroken regime. This means that the spectrum of that Hamiltonian up there is purely real. And if kappa becomes bigger than G squared, then you're breaking the PT symmetry, and complex conjugate pairs of eigenvalues appear in the spectrum of H. And the transition point is when kappa square is equal to G square, okay? This H conserves the total number of excitations, right? Because here I create one in the central oscillator and I annihilate one overall in the bath. And this doesn't change the number of oscillations, of excitations. So this makes the analysis of this here actually finite dimensional, if you wish. In fact, this H leaves a two-dimensional subspace invariant. So you have two special vectors of this ensemble of n+1 oscillators, this ES and this EB, and the span of these two vectors is left invariant by H. ES is the vector where you have a single oscillator, a single excitation on your central oscillator, and all the bath oscillators are in the vacuum. And HB is the opposite, when you have your system oscillator in the ground state, and one excitation spread equally over all bath oscillators, okay? So these are these two vectors, and because of the form of H leaves this invariant. And so the action of H really is a 2x2 matrix, because you can write it, if your initial state is within this space, then it stays within this space for all time. And here are the results of Frith and Fring. They do consider an initial state, which is a linear combination of these two guys, okay? And then they construct a square root operator S of t, such that the following holds. If you look at the solution of the Schrödinger equation with this non-Hermitian PT symmetric H, then this is equivalent to looking at a new equation with a variable phi, which is again a Schrödinger equation, but with a time-dependent Hamiltonian now. And there's a link. This phi and this psi, they're precisely linked by this transformation S. And S is designed in such a way that H of t here is actually Hermitian, okay? So Frith and Fring construct such an operator S so that this solution is equivalent to this solution with an H, which is Hermitian, okay? And then what they do is they say, okay, then they analyze a solution of this Hermitian situation. They analyze the solution. They find, they take the partial trace. This is still a wave function of all the operator system plus path. They take the partial trace over the path. They get a system density matrix, and they look at the von Neumann entropy of this here. Okay, and then they find the following very interesting picture. When kappa is small relative to G, then you are in the PT unbroken regime. And then they find that the von Neumann entropy of the subsystem of the system, when you trace out all the path, just oscillates in time. This is this graph here, as you can see. This is time versus the von Neumann entropy, and it oscillates. And then they see that if you are in the broken region, PT symmetry broken region, which is when kappa is bigger than G, then the behavior radically changes. Instead of oscillations, you have decay of the von Neumann entropy. It decays and decays to a value, a final value for T large, which is non-zero. And at the critical point, or the exceptional point, where K square is equal to kappa square, they also observe decay of the von Neumann entropy, but decay to a value 0. Okay. So we read this and we found this obviously very interesting. Namely, the upshot is that the entropy of the subsystem of the Hermitian model associated to the original non-Hermitian model has qualitatively different behavior according to in which phase you are, in which PT symmetry phase you are. But then we were puzzled and we find this mysterious because, yes, they do construct an S, right? For which they make all these calculations, they get explicit expressions, and then they get this picture. But if somebody else takes a different S, then maybe you get different curves, okay? Namely, it's easy to see. Actually, you can choose. If you give me any Hamiltonian h of t you like, I can choose an associated S that will realize this h of t in this above picture, okay? In other words, Fritz and Frink could have chosen S differently so that the resulting Hamiltonian, Hermitian Hamiltonian small h would be just 0, constant 0. You can find such an S. And if you were then to analyze the von Neumann entropy, well, nothing moves, and these curves would be just all flat, flat here, flat here, flat here, and you would not see the distinction of these different PT symmetry regimes with the other choice of S, okay? So if though you restrict your choice of S to be time independent, which is not the case in Fritz and Frink, they take a time dependent one, then the corresponding operator H has exactly this form and is S star S quasi-Hermitian, okay? And this you can do in the above model in the PT symmetric unbroken region where kappa is small, because then your H has real spectrum and there is a chance that it's similar via this S transformation to somebody who is actually self-adjoint, okay?
Can I make a comment, Marco? I think it's really important to stress that when you have the time dependence, that then your quasi-hermiticity relation, H equal to S, H, S minus 1 does not hold.
No, that's correct.
That's quite crucial. So when you speak of broken and unbroken regime, in the time-dependent scenario, you're actually referring to the time-independent case. You are getting the notion of broken and unbroken from that scenario, whereas when you switch on time, that's no longer true.
Which is obvious in the case H equals 0, because if S were not time independent, small h equals 0 means capital S equals 0.
Yeah, you're solving different types of equations. Yeah, that the equation I'm missing here. Yeah, so this H equal to S, H, S minus 1 needs to be corrected by some gauge-like term. It's I derivative of S, S minus 1. You're solving another equation. Yeah, exactly. I think that's very important to stress.
Yeah, right. So we were then motivated by this to look at this regime where kappa is small, so the symmetry unbroken regime, and trying to calculate all possible S's and to see for all possible S's what happens to the reduced density matrices and the evolution of their von Neumann entropy. Okay, so we consider kappa square less than G square. In this regime, the original H is quasi-Hermitian. Then we find the reduced density matrix of all associated Hermitian models. So you can vary over all etas, and you can also vary over all the square roots. That is, the square roots of eta then are indexed by unitaries. And then for all eta and W, we get the reduced density matrices, and we plot, if you wish, the entropy of these reduced density matrices. Okay, so I write for you here again the Hamiltonian. It's
So,
like this.
question.
Yeah.
So how do you vary over W, for example? Do you take a Haar measure, or what do you do?
Oh, it's not that complicated. It's a two-dimensional system because you have this very small invariant subspace. Okay, and then you take a unitary that lives within that subspace, and it's a 2x2 matrix. It has four coefficients. It has four coefficients.
So do you take all of them equally probable?
No, I don't distribute them or anything like that. I just simply write down a formula for all 2x2.
So parametric, you will.
Parametric.
Okay.
He just constructs all solutions, Joshua.
Yes.
Okay.
Yes.
Okay.
Yeah, it's a game of parameters. Okay, so this is the Hamiltonian. The spectrum is given here. And you see that if you are in the symmetry unbroken regime, then this kappa is small relative to G, then you get here a positive number, and your spectrum has two real eigenvalues. You are in a two-dimensional system, two-dimensional space spanned by these guys, two distinct eigenvalues. So you can certainly write your H in this spectral representation, if you wish. Here are the eigenvalues, and here are eigenprojections. And these V plus and V minus and V star plus and V star minus are eigenvalues of H and H star, and they form a bi-orthonormal basis in this two-dimensional invariant space where H acts on, okay? And so from what I said above, you know all the metrics associated to this. This is the set of all the possible metrics. You have to take the projection onto these, onto the eigenvectors of the adjoint H dagger, and then you can mix them up with any positive coefficients. Each matrix like that is exactly one metric operator associated to H. Okay, then we calculate the reduced density matrices. We take an initial state from the given two-dimensional subspace. And just to remind you, in the non-Hermitian system, the dynamics looks like this. It's given by the original non-Hermitian H. In the Hermitian system, the dynamics is given by the Hermitian H, which is obtained from the non-Hermitian one, using this map S, which is the square root of the metric operator. You take the two reduced density matrices. This is the one for the non-Hermitian situation. This is the one for the Hermitian one. And of course, the one for the Hermitian one depends on the choice of H, which is the choice of W. Okay. So what are the parameters? The metric has two parameters, x1 and x2, right? Let me scroll up again, because this is the set of all metrics. What I can vary here as I wish is x1 and x2. Other parameters are the unitary that I can use in the construction of the square root operator. And here it is, 4 parameters. Of course, they're linked because this is supposed to be a unitary matrix written in the spaces of these two ES and EB vectors. And then we can also parameterize the initial state by two numbers, A and B, because, well, that's how our initial state is taken like. And of course, there's a constraint between A and B and all the other parameters, in fact, we want this to have H eta norm equal to 1. And when you make a calculation using all these parameters and you calculate the reduced density matrix of the non-Hermitian model, well, then you get simply this. You get a diagonal matrix in the basis 0 and 1. This is now a basis of a single oscillator because you have traced out all the bath oscillators. This is the ground state of a single oscillator, and this is the first excited state of the single oscillator. Okay? You get a density matrix that is just diagonal in this basis and has population P and 1 minus P on these levels.
There's a question from Miloslav.
Yes.
Yes, I have a comment on this W. You wrote W is equal to W dagger, but you say it's unitary, so it should be to -1.
Oh,
Just
Jesus.
listening.
Very bad. Thank you.
Yes, thank you.
No, unitary, not equal to -1. The dagger has to be the inverse. Okay. All right, so then you calculate these quantities. You can do this all explicitly. You can calculate these, well, there's only one quantity, which is the population, but it turns out that this population is actually a complex number, except if you choose the metric exactly so that these two weights of the two projections are equal x1 equal to x2. Miloslav has still his hand up. I don't know if he still wants to ask something or if this is from before. Anyway, so if we want this to be a true density matrix, we should look at the metric for which this condition is correct. So we look at this case. So these two parameters are now melted into a single parameter, which characterizes the metric. Then the reduced density matrix of the non-Hermitian problem has positive spectrum, and the von Neumann entropy is well defined. This is it, right? It's trace rho log rho. In terms of eigenvalues, this is the formula here. P and 1 minus P are the two eigenvalues of this two-dimensional density matrix. And then finally, we're going to compare this with the density matrix of the associated Hermitian system. Okay, and we calculate these density matrices, and they also are diagonal in the given basis of a ground state and first excited state of a harmonic oscillator, with again populations Q and 1 minus Q that are equally well explicit in terms of all the parameters. Okay, and so the first thing you can ask yourself, well, how do the two density matrices, the reduced one of the Hermitian system and the non-Hermitian system, compare? And we show something, which is that these two density matrices are the same only if you choose your square root or your W within this square root to have a very specific form. Namely, it should be diagonal, and on the diagonal, it should have two phases. Okay. So generically, when you choose A, B, C, and D, or the unitary W sort of randomly, it's not going to look like that. And these two matrices, density matrices, will not look the same. And so we were hoping then that there's still some sort of universality in these density matrices, even though when you vary W, hopefully some quantity will stay the same. And as I will show, we might have found something like that. Okay, so then we looked at the evolution of the entropy, first of all, of the reduced density matrix that you obtain from the non-Hermitian system, okay? So the eigenvalues there were P and 1 minus P. It's a two-dimensional density matrix. And the P is explicitly given by the formula that you see here. There's actually only two parameters that are involved. There's omega, which is a frequency with which this population oscillates. This is an open system, but it's kind of a finite system in the sense that, you know, the spectrum of the total Hamiltonian is only point spectrum, so everything is oscillating. So the oscillations are given by the frequency which I show here. Kappa is smaller than G, so this is strictly positive. And then there is another sort of parameter that is involved, which is this parameter alpha, which is a real number that can take values between 0 and 1. And it combines information of the metric x, the initial condition, which is given by this parameter a, and the parameters of the Hamiltonian, which is this square root there. Anyway, what we find is the following. Okay, so let me explain this picture. So there's three very special points of this parameter alpha, which is alpha equals 0, a half, and 1. If alpha is a half, then you can see that the time dependence totally goes away. And so for alpha equals a half, you get exactly actually a stationary density matrix. This is a very special case in which the metric, the initial condition, and the parameters of the Hamiltonian work together in such a way to get a stationary state. So that's this picture here. In orange, you see the entropy, and in dashed blue, you see the population. For alpha equals 0, it's also a very special case because it means that this coefficient a must be 0, and it means that you start off with an initial condition in which the excitation is just in the bath. You get this picture. So you see that you have oscillating populations and oscillating von Neumann entropy. And the generic case actually is sort of this here, when alpha is anything but 0, a half, and 1. And then you get this picture. And what you see is that the periods of the population and of the density and of the von Neumann entropy, they are different. The period of the population of the density matrix is half of the period. This wiggles quickly, but the entropy wiggles much slower. The frequency is divided by half, or the period is doubled. Okay. There's a symmetry between, alpha and 1 minus alpha. So actually, these pictures below here are subsumed in the above pictures. So I'm not discussing that. But the point here is that for the evolution of the reduced density matrix of the non-Hermitian system, this is the point. The period of the population is twice the period of the von Neumann entropy. Okay. Then we look at, that was for the quasi-Hermitian system. Now we take the Hermitian system associated to that, take the reduction, and plot again the populations and the von Neumann entropy. Okay, we have again the special cases, of course, alpha equals 0, a half, and 1. And now we have an additional parameter. This is this parameter C, which labels the unitary W. Okay, this parameter, let's take it between 0 and 1. It could be complex, but let's take it only real, that it can vary between 0 and 1. So this W is actually just encoded in this number C. Okay, and here there's the other parameters alpha, the same as before. So we see that unless you're in the special case alpha 0, a half, and 1, this is the generic case. What you see now is that suddenly the populations and the von Neumann entropy, they oscillate at the same frequency. They have the same period. Okay, you see, one period here is one period here. While before, for the non-Hermitian case, one period of the population was 2 periods of the von Neumann entropy. Okay, and this is actually, this thing happens not just for this C equals a half, 0.5 in this picture, but it happens for all C. And this is kind of the upshot of that. Regardless of the choice of W, when we pass from the quasi-Hermitian to the Hermitian situation, all the Hermitian associated systems, they have the same period in their entropy. And that period is exactly double the period of the entropy of the non-Hermitian system. Okay, this is, as you can see here. So this is the generic case, alpha not the special guys. So here you see that in the quasi-Hermitian situation, you have fastly oscillating entropy and less fast oscillating entropy in the Hermitian systems. And all of the Hermitian ones have the same frequency. Okay, so I would like to end by sort of, this was just a picture that gave you what I'm saying, this doubling of the period, right, for specific alpha, but it's actually not hard to see what the mechanism is. I'm not saying that I know the physical origin of this, but the mechanism of why this happens is not hard to understand. And that's how I would like to end. So we have the parameters alpha, which encode the metric, the initial state, and the parameters in the Hamiltonian, this G and this kappa, right? We have another parameter C, which tells you what kind of choice you make when you pass from the non-Hermitian to the Hermitian. And when C is equal to 0, it means this unitary basically is the identity. Then the two density matrices, reduced density matrices coming from the non-Hermitian and the Hermitian problem are the same. Okay. So if you look at the population of the general, for C general, Hermitian situation, reduced density matrix, it looks like this. There is a central point Q0, and the population oscillates with a frequency 2 omega around this, and has an amplitude of whatever, delta here, okay? And Q0, which is the center of where the populations oscillate around, depends on the parameters. It depends on alpha, but it also depends on C. So if I vary if I select all kinds of Hermitian systems associated with non-Hermitian ones, I vary C, and so this Q will vary. Okay, and the amplitude will also vary. But the point is that when C is equal to 0, which corresponds to the non-Hermitian situation, this Q0 is exactly a half, because you see for C equals 0 or 1, there's a symmetry. This here vanishes, and this Q0 is equal to a half. Okay, and so if I plot, this is a plot of the function. I hope you can see it. I can make it. No. This is the plot of E of Q, which is the von Neumann entropy as a function of Q, which is just minus Q log Q minus 1 minus Q log 1 minus Q. That's this function, right? Of course, the entropy is maximal for a two-dimensional system if the population is a half, and then it's symmetric like that. Okay. So as I said, for C equals 0, when your unitary W is just the identity, and you reproduce the quasi-Hermitian situation, you oscillate with your population around Q0, which is a half, and then you oscillate like that. What does this mean in terms of the resulting von Neumann entropy? Okay, so I start here with my oscillation. I will do one period. I will start here at time 0, then I go to a maximum and come back to a minimum as time is 2 omega, which is the period. And I check what happens with the von Neumann entropy. This will be the curve Y. If I start here at time 0, this is my, I read off here, the entropy, it's minimal within this picture. Then I increase my population to reach its maximum, a half. That's when the entropy is max, that's the 0.2. Then I decrease down, right, to the original minimum. Here I am. And then I have to go back to reach a whole period in the change of Q. So when I go back, I go again through one maximum here, which corresponds to this, finally to my initial state back of the population here. So one oscillation in Q equals 2 oscillations in the entropy. That is because C was 0, that is Q was centered at a half. If Q0 is not centered at a half, then you are in the situation of the Hermitian derivatives, if you wish, of the non-Hermitian one. So here I took a Q0 for illustration that is 0.6, that's not a half. And the population oscillates like this. Now, if I do the same graph as above, well, I start here. So I start with entropy here, then I move up to the maximal entropy that's here. Then I move down to the minimal entropy that's here. And then to complete the whole period, I have to move back. But when I move back, I just move back up again. And so to one oscillation here of the population corresponds only one oscillation of the von Neumann entropy, not 2 as above. That's because the center around which you oscillate does not coincide with the center of symmetry, so to speak, of this function E of Q. Okay. All right. So let me summarize. It is not new, of course, that if you have one Hermitian system, to that you can associate many. This should be quasi. One quasi-Hermitian system, to that you can associate many Hermitian ones. Non-uniqueness of the metric and of the square root of the metric, which define the Hermitian system. And what we do here for a simple model, we calculate all Hermitian systems stemming from an explicit open quasi-Hermitian system of interacting oscillators. We show that the reduced density matrices, the reduced density matrix of the quasi-Hermitian situation is only truly a density matrix for a unique fixed metric. And then for that metric, we can compare the von Neumann entropies of all the Hermitian systems obtained from the non-Hermitian one. And we see that the period of the von Neumann entropy of all reduced Hermitian systems are the same, and they're exactly half of the period of the quasi-Hermitian system. Okay, and so this is what I had in mind to show you, and I would like to thank you for your attention.
Thank you very much, Marco.
Thank you, Marco.
Comments, questions? I have an obvious one. What happens in the broken regime, Marco? And at the exceptional point?
Well, what happens is a good question. Because, look, sorry, I'm scrolling up, don't get busy. We didn't analyze this. Why did we not analyze this? Because if you want to do this in the broken region, then you have to make S time dependent, right?
Yes.
But if you make S time dependent, then there are so many choices. I can choose anything. I can reach any Hamiltonian H of t by making a choice of S. So I don't even know how to start an analysis because I can get anything I want. So in what you do, somehow you chose a right S that distinguished, had the different sort of behavior of the von Neumann entropy in terms of the regime, of the PT symmetry regime. But I just don't know what the right choice is. There's too many choices here, so we didn't sort of know how to reduce this amount of choices to something that is classifiable. You know what I'm saying?
I mean, this is what we were excited about, that you can make sense of that regime, yeah, because that normally doesn't work. Yeah, I mean, I can see it's difficult to classify, but it would be interesting to see, because we were just happy to find one solution. Yeah,
absolutely. Yes,
so you
yes.
now have so many solutions. Would be interesting to see if there are solutions that exhibit a totally different behavior. Yeah,
I agree with you. Yes. Yeah. Yeah, we didn't look at that for the reason I said.
It's difficult to pinpoint it, but you could find a set of solutions, maybe not all, but you could find quite a lot of new solutions in this way. Yeah.
Yes.
But this wealth of solutions, this non-uniqueness, or I don't know, not well-posedness of the problem, does it have physical meaning? I mean, does each and every S, time-dependent S, correspond to some protocol, some non-equilibrium procedure that I can drive my system, and therefore that would explain the non-uniqueness?
I do not know the answer to this. I do know that you can choose, you can choose S's that are, for example, of product form, right? If your S is some S1 or S system times SB, then you get something. If you choose it not to be like that, the physics will be different, because in your S, you actually entangle, in this mapping, you entangle the subsystems. And so the von Neumann entropy will look very different.
Okay.
But sort of the point, I think, here is that no matter what S you take, one universal thing is that the period of the von Neumann entropy is the same, no matter what S you take. That's a constant thing. And it compares as being double the one.
And do you expect it to hold also beyond this particular model that you studied? Is it a general conclusion?
I don't know. Yeah, it will be. There are other, there's also relatively recent paper by Frith alone, where he studies two James Cummings models that are coupled and studies the entanglement in a similar way. So one could certainly look at other models that are hopefully well treatable, in the sense that you actually can make a lot of calculations more or less explicitly, because you have all these parameters, and see whether this constancy of the period over all Hermitian realizations is actually still holding for other models. At the moment, I do not know, yes, but it's something one should check. Yeah.
Thank you.
Miroslav.
Yes, thanks. First of all, I must appreciate very well prepared talk and very clear and using nice examples. My comment is that it is showing the wealth of possibilities behind the formalism of non-Hermitian operators. And what I see as a key point is that the concept of PT symmetry is usually connected with the concept, now we see the transparency I need. I mean, this H, capital H, and this transparency we see is an operator which generates expansion, time evolution of the psi wave function, but it is just representation of Hermitian translated to non-Hermitian case. And in time-dependent case, it is something like analog of Dirac represent. I mean, interaction picture of quantum system. So that's why what we know from textbooks, and you work with Hermitian operators, you have unitary evolution, and you have just interaction picture as rephrasing the same picture of evolution, which is unitary. But if you speak about open systems, you have something else in mind. That's the point. And if you speak about PT symmetry, you should, in stationary case, have in mind sort of technical help to construct these S operators and eta operators, which form the theory, which is just one quantum mechanics. But now when you start speaking about capital H, you speak about two different formulations of quantum mechanics, and it is very exciting to be able to transfer mathematics to open system theory. And in my eyes, the use of PT symmetry in this case is opening new language and new meaning of things. Because if you stay with old meanings of things, so your operator, small h, is transformed to energy operators, temporary energy operator, which is still observable, while this upper case h is not observable. That's a key point. And because it's not observable, so you formulate the theory which I must admit I don't understand. I mean, in this case, I don't know why one speaks about PT symmetry, because PT symmetry should concern just symmetry of models in Schrödinger picture, but in Dirac picture, in interaction picture, I gave a use of this capital H may be complex and still evolution is unitary. So that's my comment. I must repeat that your talk was very clear and compatible with all my views of how we understand quantum mechanics of unitary evolution. And this picture using 2x2 matrices makes it very explicit. So all your statements I may support. I mean, it was very well done. Thank you.
Thank you very much. Thanks.
More comments, more questions.
Yeah, can I ask a question about the physics underlying some of this?
You can always try. I don't know if we will know the answer, but yes, sure.
So the entanglement entropy is sort of in the eye of the beholder. So it really depends how you choose to separate your total system into different subsystems, and so somehow your S is separating your system, your total system, into different subsystems. Do you have a feeling for how that is occurring here?
Well, so we start off with, I mean, the separation into system and path is given at the very beginning, right? I never changed that. This is it, right? I have a single oscillator which is in contact with n other oscillators. So the Hilbert space of the single oscillator is the Hilbert space of a single oscillator, and H path is the Hilbert space of all these. And so you have a tensor product between these two. This is system and path. So it's bipartite, and I'm never going to change this, right?
But there must be something more than that. I mean, you're treating them in different ways, I suppose. Maybe each of these oscillators, you're adding different phases to them or something in this S.
Oh, well, Right. So
maybe what I'm saying is completely obvious to you, and I'm just asking you to restate some.
no.
Yeah.
I mean, this S is acting. How should I? So right, total Hilbert space is H system tensor H path, right?
Mhm.
And this S here acts as an operator on here. And indeed, this is a good question. I'm not taking this S to be of product form or not of product form. I don't know. I'm taking a general S. And so some of the S's I look at, they may be of product form, some maybe not of product form. It all boils down to a single parameter C. But what I see is that no matter how I vary this C, whatever, the period of all these choices of S of the von Neumann entropy, which has to do with entanglement, obviously, is still always the same.
Yeah, that's remarkable. Yeah.
Another quick technical question. In the simulations, in the numerical simulation that you showed, results that you showed, what was N? How many oscillators were in the bath?
It doesn't matter because I'm not sure. It doesn't matter, but all that N does is speed up the time. It has no other bearing. Look, I can also show you with.
No, because there is asymmetry in the exchange of quanta between the system single oscillator and the bus, which is the N oscillator. So if N is very large, this asymmetry shouldn't be too important, I would say.
Look, all I can say is that if you look at the eigenvalues of the Hamiltonian.
Yeah.
Sorry, I want to see the pictures of Frith and Fring here. You can see the effect of.
Okay.
It's just really what's it called? Stretching the time variable. Okay. So this is a different end. So for n equals 2, your revolution is slow. For n equals 50, your revolution is the same, but it's much quicker.
Okay. Thank you.
It just scales out. It scales out, and it goes into the time axis. It's just a stretching of the time.
Okay.
I suppose it's significant that it's this harmonic oscillation.
Well,
and if one had a non-linear sort of
well,
behavior of this oscillation that wasn't a sinusoid.
Yeah, but this is a more difficult question. Let's answer the easier questions first.
Yeah.
May I ask a question? It's Uwe Günther here. Concerning your tensor product representation and so on, this is clear. And you are keeping, in all your considerations, you are keeping in a subspace of fixed total particle number.
Oh, absolutely. We're in a one excitation submanifold. So let me flash here. Okay, so we're in this setting where you have one total excitation, and not even that. The excitation is only either on the system oscillator or spread equally over the bath oscillators, okay? Because that is just a very simple subspace that's left invariant by this Hamiltonian.
Yes.
So the Hamiltonian leaves.
That's clear, but anyway, you can also fix just some particle number subspace, suppose, and not some subspace, and then all your system is acting in this subspace.
Yes.
Yes, and I'm very much that intuition tells one that actually one can just work once you are restricted to these subspaces. You probably can work within or map all your setting from this one oscillator and n particle or n oscillator above to a kind of via Schwinger mapping just to some SU2 or SL2 algebra representation, as we did it in our paper on this Bose-Hubbard model. And in this case, everything boils, of course, down to matrix representation. This is clear. But in this case, you can probably use also the setups that Andreas and his collaborators did work with in just a Lie algebra representation and do all this in this Lie algebra representations actually.
Mm-hmm. But
most likely, I may be wrong, of course, but intuition tells me that this might work in this case, and so everything should be treatable analytically within this dynamics in Lie algebras. And this would be very nice to have it similar like Andreas did it, but just in a slightly different regime here, probably. But maybe I'm wrong, so I'm not absolutely sure, but it's most likely 80%. I'm sure that it will work in this way.
I mean, one of the difficulties is to keep track of all the possible choices, right? And so, of course, if we increase the dimension, then this becomes much more complex. But maybe
yes, but you have this underlying Lie algebra structure, and this is very strongly restricting. And all you are changing is just the representation. You can just work in the fundamental representation. Everything goes through. You can solve this differential equations and so on within the Lie algebra simply by fiber bundles over this Lie algebras. And then you will have all the tools, and you can just check in which concrete n particle representation you are working, and so it should go smoothly, very exactly, analytically. Okay. It would be very nice to see this explicitly.
Yes.
For the general case of a fixed particle number for a total system.
Yes, yes.
This is
okay.
Do you know about if representations of this tensor product representation, how it's fitting with this Lie algebra business and so on? Did you try this somehow?
I did not try this. I have seen some of these papers, but I can't say that I'm expert enough to know how to phrase it. Yeah.
Oh, okay.
At this moment.
Thank you anyway. Very nice talk. Okay.
Thanks.
I think it's a direct sum of SU2 then.
Yeah. Might be, yes, might be.
Miroslav.
I have another comment. This ambiguity depends or is related to what people sometimes say. It was mentioned in the beginning that there may be other observables, other candidates for observables introduced into the theory. My question is, would you consider something like that?
Well, as far as I understand, I don't know what you mean by other observables, but once you fix the observables, then the metric is fixed, right? But then you still have the non-uniqueness within the square root of the metric.
Yeah,
Of course, but you know, your parameters are dependent on precisely that. So if you have this freedom in W, if you have this freedom in the parameters, there may be some physical input. Once you have in mind oscillators, I mean, there may be something which you introduce as a requirement by physicists. Something is observable.
But wouldn't that just fix the metric, and you would still be able to choose W as you wish? So,
but I would understand better what is the difference between closed and open system, because there is just one quantum mechanics, and there is also possibility of study open system by this mechanism which you showed. So that's something which are two very interesting alternatives for development of the mathematics.
yes.
So some part of this ambiguity may be connected with what one understands by other observables of the system.
Of the system, yeah, okay. If you talk about local observables, yes, that's maybe a good point. Yes, the metric is defined by global observables, but if you define local observables, then maybe this fixes W somehow. Yeah, okay.
Thanks.
More comments, questions? If not, then let's thank Marco again. Thank you very much, Marco. Very nice and clear talk. Thank you.
Thank you very much. Appreciate it.